let's let's take a step back real quick and think about uh, this circuit. We've got a capacitor. It doesn't matter if you've taken circuits or not. The concepts here are still pretty easy to get the first time they're explained. So we've got a capacitor, and we've got a resistor, and we'll just say that this is going to ground. And let's say that we introduce a voltage here. Now, what you can think is this resistor is kind of acting like a bottleneck for charge, right? It resists the flow of charge. That's why it's called a resistor. And a capacitor, well, as the name also implies, is something that has a capacity for charge, meaning that it can hold some charge. So this resists the flow, and this holds the end of the flow, right? It's kind of like a bucket for charge. And so what that means is we get a buildup of pluses here, and we get some minuses here, right? I guess we'd have the equal amount of minuses there. But the thing is since there's this resistance here, this takes time. Charge takes time to flow. And so if we were to measure the voltage of this capacitor, or how close it is to being at capacity, it would kind of look like this. Let's say we're zero capacity, and then we introduce our voltage, and then we might end up with something like this. So this takes a certain amount of time for it to get close enough to consider it to be charged, right? So this is a time t. So given this context, let's think about what's happening with an NMOS transistor. The same thing happens for PMOS transistors as well. So we've got our gate here, and then we've got the rest of our transistor. And even though we don't draw it, these lines have some resistance, right? There is some, that's a really bad resistor, but there is some resistance here. And also, this is a capacitor. There is some capacitance here. And if we remember the way that NMOS, PMOS transistors work, there's also some charges moving around inside of the transistor as well when we apply voltage here. And so what that means is that we know that when we apply a positive voltage here, that charge will be able to flow. Well, I guess really it's negative charges can go this way, but we know that given this model, that this doesn't instantaneously close or start conducting. It takes a while, it takes a certain amount of time for it to completely conduct. And so this is what causes propagation delays, right? If I have an AND gate and then say a NOR gate and maybe a NOT gate, and I say these are two zeros and this is a 1, if I change this 1 to a 0, say this is at time unit 0, it is not going to instantly change on the output of this NOT gate. It might take one time unit to change, and the OR gate is also going to take some time to realize that there's now a 1 there, and it might take another time unit. And so that time unit is going to be, some significant portion of how long it takes for this whole thing to charge up, or really what we mean is reach steady state. This is changing or transient, where this area here and this area here are our steady state. And so that's why gates will have their propagation delay, or their rise and their rise and fall time will be listed, and that's just something that you need to design around, or kind of that helps dictate the frequency that you can run your circuits at, or the time provisions you have to make.